So we have the pleasure to have Pravesh Kothari, who is from Carnegie Mellon University. He will talk about algorithmic robust statistics, the sum of squares. Please. So yes,
Okay.
again, yes, the questions can be asked in the chat as before. Please.
Okay, yeah. Thanks, Bernard, and thanks to the organizers for inviting me to this great workshop. I had a real good time watching the talks today. Of course, like everyone else, I would have wished to be in Germany, but I'm in India. But you can see my background is Carnegie Mellon in Pittsburgh, so that's how things are these days. So, just for context, I actually work in this area of algorithms and complexity. So even though my talk, uses many of the same methods in a certain sense, similar to, let's say, Lorenzo's talk, my perspective is that of algorithm design. And so in this talk, I'll show you how methods from real algebraic geometry and, specifically polynomial optimization methods can actually be used to design new and better algorithms for problems at the intersection of algorithm design and statistics. And I'll explain, what this area is. It's a pretty new development in computer science. So hopefully you would, enjoy learning a little bit about this. My ulterior motive, and also the way I've structured the talk, is to actually get to two main open problems in this area. And because this is like a newish area, these open problems are, aren't like, 30, 40-year-old problems, just like, 2-year, 3-year-old problems. But the nice part about them is that they are squarely in, the expertise of people, who are joining this workshop. So they are basically, in a certain sense, statements in real algebraic geometry. And so my, optimistic hope is that, we'll be able to make progress on some of these questions. But, at the very least, I'd be able to tell you about how polynomial optimization is, one of the centerpieces of this nascent area of work. Good. So with that prologue, let's begin. So the problems that I'm going to tell you about, so what I'm going to do is, give you like a very high level overview of problems, results, and methods in this area of algorithmic robust statistics. And then, with the hope of getting to these two open problems that I just mentioned. So the context of this work is in this area called robust statistics, which is really an area of, statistics. So let me explain to you, what are people interested in this area. So you may have heard or even know very well that when we are trying to fit, or when we are trying to learn from data, which many people seem to be doing these days, the mathematical problem that we actually try to solve is that of fitting a certain statistical model to data. Okay, so you may have heard of models such as linear regression, or somewhat more complicated models like Gaussian mixture model, and so on. It does not matter whether you know what these are or not, just the basic idea that there is a probabilistic model that you fit to data, and fitting just means that estimating the parameters of this model. That's roughly sufficient for our purposes. So when you try to design algorithms to solve the fitting problem, you assume that the input data that you have is an independent sample chosen from the statistical model that you've decided is the right one. Okay. Now, it doesn't take that much of thought to realize that this is a idealized assumption. The input data that we see has no special reason to really behave like an independent sample. And so it's natural to ask if the algorithms that we design, work gracefully, even if, the data is not exactly, an independent sample, but deviates from it in some ways. This is not at all a new question. This was asked by like famous statisticians like Tukey and Huber about like 50, 60 years ago. And, two natural situations that they imagined this could happen is data corruption. What that means is that, imagine that, in the beginning, you did really have an independent sample, but then, before it was actually given to you, there was like an adversary sitting in between you and, the data, and the adversary managed to corrupt some, fraction of points in the input data. So now there are like outliers or, corrupted subset of points. Or for example, imagine the situation where, you just guessed the statistical model almost, but not quite right. So, the actual model is just a little bit different in some precise sense from the chosen model. And so the question you would ask is, what happens if, the input data is only approximately, satisfying your assumption, but not exactly satisfying your assumptions? So it turns out that, our natural algorithms actually really fail drastically in such situations. And so, what Tukey and Huber began is this whole area of robust statistics, which is focused on designing estimators or algorithms that are resilient, to various kinds of modeling errors, like minor modeling errors. Now, this is basically a classical area of work in statistics. The reason we are interested in it, the reason, there is like this new line of work is because the algorithms that come out of this line of work tend to be computationally very expensive. They typically run in time which is exponential in the dimensionality of the data. And so, what we are interested in is designing much faster, efficient algorithms. And efficient for the purpose of this talk would roughly mean, let's say, polynomial in the dimension. So the running time or the algorithm's time complexity should be a fixed polynomial in the dimensionality of the data. That's what we're after. And so, that basically is the goal of this talk, algorithmic robust statistics, where we want to design computationally efficient, meaning polynomial in the dimensionality, robust, meaning that, our algorithms should continue to work even if the data, deviates from the assumptions tiny bit. And our hope would be to get as good an error as statistical considerations permit. Okay, so that's the goal of this whole area of work. Specifically, today I'll focus on mostly on the so-called strong contamination model. Actually, I'll also maybe touch upon a slightly different model, which I'll describe to you in a minute. In the strong contamination model, here's the setting you're interested in. Okay, you're solving this problem of learning some parameters of some probability distribution. And so you imagine that there was like an IID or independent sample constructed from this distribution. Let's call that sample X. And I'll always think of such sample as, n points in d dimensions. And, remember, we are supposed to think of d as a growing parameter. So we are interested in, being efficient in the amount of work we do in terms of, this dimensionality d. Now, as I said, in this setting, you don't quite get access to X itself. Instead, you get access to a corrupted version of X. And so what you get access to is Y. And the only property you know about Y is that Y intersects this unknown independent sample X in all but in all but epsilon fraction of the points. Okay. So the remaining epsilon, and think of epsilon as like a fixed but tiny constant, like 0.1. So this 10% of the points are completely arbitrary and even like adversarially chosen outliers. Okay. Given such a Y, your goal is to, solve the problem of estimating various parameters of the distribution. This could be something really simple like estimating the mean of distribution D, or, covariance of distribution D, or, you could be trying to solve somewhat more complicated problems like linear regression or whatever. Okay. All those problems are basically, in the purview of the interest of this talk at the moment. Okay. So just to make this model absolutely clear, let me take this, very simple example of estimating the mean of a distribution D. Okay. So the setting is the same. You had a unknown IID sample X, but then it was corrupted. And let's say 10% of the points in X were like arbitrarily corrupted. And so what you now see is Y. And your goal is to estimate the mean of the distribution D. Now, very basic statistics shows that if there was no outliers, meaning if you got access to X itself, then simply taking the empirical mean of X, that is just averaging the points in X, would give you an estimate of the mean, which is reasonable. And you would need some basic assumption like the covariance of the distribution. On the other hand, this estimator completely breaks even if there is like a single, like 1 point, which is an outlier in Y. So even if Y changes exactly 1 point in X, you might actually get into trouble with this particular estimator simply because this 1 point could be way out there. And, it could really have a huge influence on the empirical mean. Okay. So point I'm trying to make is that in this setting, even mean estimation, which can be thought of as a really simple task, becomes really challenging. Okay. So that's, that's going to be our, one of the main goals today. And I'll tell you some of the ideas that go into designing algorithms that work in this strong contamination model. The other model, which I will get to if I have time in the end, is the list decodable model, which is like a variant of the strong contamination model, where the only difference is that instead of 10% of the points being corrupted, 90% of the points are corrupted. In other words, only 10% of the points, are from the original statistical model that you had chosen. The rest of the 90% were just basically, added as adversarial noise meant to throw you off. Okay. Now this setting looks kind of weird. How can we even hope to recover anything when like more than a majority of the sample is like outliers or, just noise? So it turns out that in this case, we can't hope for like uniquely recovering the parameter we are interested in. Instead, we can hope for recovering like a small constant size list where the constant depends on, the fraction of data that is good. So if 10% of the data is good, let's say you would be okay with finding a list of size 100 of candidate parameters such that one of them is close to the truth. Okay, so that's all in some sense you can potentially guarantee in this setting, and that's what you would actually like to achieve. Okay, so both these models were, in a certain sense, are quite natural, and one might imagine that they should have been studied like forever, but it turns out that they were actually somehow not studied for a long time until like these, a couple of very interesting works began investigation of these two models and more generally robust statistics from an algorithmic perspective about 5 years ago. And since then, this area has exploded. By some estimates, there might be, as many as like 200, 300 papers in this area in just last 5 years. And so, that's basically my goal, to explain to you, what this area is all about. Well, to be perfectly honest, I'm not going to tell you about all of this area. I'm actually going to focus on the usage of moment SOS relaxation, or this Lasser-Perillo hierarchy of semi-definite relaxations of polynomial optimization problems, and the usage of this method in the context of problems in robust statistics. And so the punchline, which hopefully I'll tell you a little bit about through the talk, is that even though there are other methods that obtain great algorithms for this problem, the algorithms that are based on the sum of squares approach are by now the most general, as in like they work for the most widest possible class of distributions known, for each of these tasks. And so, you get like algorithms that work under the least restrictive assumptions if actually you work with the sum of squares approach, and I'll try to explain to you why and how that actually happens. So, with that brief prologue, I can explain to you what my goal, or what the purpose of my talk today is. So I want to explain to you, how like a bunch of results, the names of which are mentioned here. This slide is basically to convince you that there is at least a bunch of problems that can be solved using the sum of squares method. So the talk actually is motivated. And so what I want to tell you is like a general blueprint of how you can think of each of the algorithms based on the sum of squares method for problems in this area. And I'll focus on one key technical engine that makes this algorithm design paradigm work. And this technical part would also lead to two natural open questions that I mentioned at the beginning of the talk, which could benefit from methods from real algebraic geometry and could likely improve several algorithms at once. Now, because I'm focusing on this overview style thing, I would actually not have a complete proof of any statement I make today. That's a compromise I'm gonna stick with. Good. So, okay, that's like the first part of my talk. So if there are any questions, I can stop here and take them. Otherwise, I can go ahead and tell you more about strong contamination model and how SOS plays a role.
No question in the chat.
Okay, perfect. So let's go on. So what I'm going to do now is tell you, how a generic algorithm based on the moment SOS relaxation of polynomial optimization problem roughly at a high level looks like for solving a robust statistics problem, okay, in the strong contamination model. So remember the setting. We had an original sample X from some distribution D that we never got to see. We instead got to see like a epsilon corrupted version of X. So, we got to see this Y. The only guarantee on which we have is that Y intersects X in like 1 minus epsilon fraction of the points. And our goal is to estimate, some parameter of distribution D by looking at Y. So, our algorithm can only access Y. Okay. So here is how, a blueprint of algorithm design for such a problem, such a generic, class of problems looks like. The first step, and I'm going to draw some picture for you to hopefully help understand this paradigm. So the first step is going to be to make some reasonable assumption on the class of distributions that D comes from. So I don't quite know what distribution D itself is, but I'm going to think that it's going to come from some reasonable class of distributions. Okay. Now notice that this is kind of necessary because if I make no assumptions, then for all I know, even the corrupted sample y, could come from some other distribution. So there would be no way for me to distinguish between, true samples and corrupted versions of original samples. And so some assumption on the distribution or the class of distributions is clearly required. So let's say you make that, okay? And pictorially, let's represent that by, this black egg-like thingy that, marks the reasonable class of distributions that we think D comes from, okay? Okay, so X is like a sample X is the original sample we see, and X lies in this ball because it's a typical sample or like a size n sample from a reasonable distribution D, okay? Now, of course, we don't actually get to see X, we get to see Y, and in general, Y won't be in this ball. The only guarantee on Y that we have is that Y intersects X in 1 minus epsilon fraction of the points, or equivalently, Y is at most epsilon far away from X in normalized Hamming distance. Okay, very good. So here is, how the generic algorithm looks like. Okay, and it's going to be a very high level outline. I'll explain to you, I'll explain a little bit more to you how it actually relates to an algorithm very soon. So for a second, forget about efficiency considerations. Forget about, designing efficient algorithms. Let's just think of, spending whatever amount of time we would require in order to solve this problem, okay? Then here is what you could do. You don't quite know X, you only know Y, but you know this class of reasonable distributions. So what you could try to do is try to find a size n sample X prime, okay, that comes from a reasonable class of distributions, okay? So X prime should be inside this ball, and it should satisfy the only property that I know X satisfies, which is that X and Y are at most epsilon far, okay? So I would want that X prime and Y should also be at most epsilon far, okay? In other words, I try to hunt for X prime, which is a reasonable, which comes from a reasonable class of distributions and is at most epsilon away from Y, okay? And then I'll simply output the parameters of X prime, okay? That's it. That's my meta algorithm, if you will, okay? And here is, how the meta analysis looks like. The first observation in the meta analysis, and I'll very soon, give you an example to make sure that this sticks. But, going on, the main observation is that the only thing I can guarantee, about the relationship of X prime to X is that since X prime and Y are at most epsilon far, and since X and Y are also at most epsilon far, X and X prime cannot be more than 2 epsilon far. Okay, so I know that X and X prime must intersect in at least 1 minus 2 epsilon, fraction of the points. Okay, so the analysis basically, involves proving the following. So, whatever parameter you're trying to estimate, you would like to bound the distance between that parameter when computed on X and when computed on X prime, given that X and X prime are at most 2 epsilon away in Hamming distance. Okay. And so, and okay, so I'll soon give you an example of this, but, if you could bound the distance of the parameters of X prime from the parameters of X, given only that X prime is at most 2 epsilon away in Hamming distance from X, then in certain sense, that at least if you could do this, highly inefficient search, you would at least be successful in getting some reasonable bounds on the estimates for the parameters of X. Okay. Now, in order to make this whole outline efficient, and here's where real algebraic geometry and polynomial optimization methods enter, we actually need a certain efficient representation, certain algorithmically efficient representation of the class of reasonable distributions. And I'll explain to you what this means in a second, but the buzzword for it is that you would have to find a sum of squares certificate of membership in the class of reasonable distributions. Okay. And at the moment, you can roughly think of it as, a semi-definite. So in particular, an efficient convex representation for the class of all reasonable distributions, where reasonable is, whatever you've chosen in bullet point number 1. Okay.
There is one question.
Yes.
Chat. By Alexander. Maybe you can ask. The question?
Alexander?
Yes. So, hi Pravesh. Sorry for sneaking into this conference. I still have to register. But the thing is, I wanted to ask you where you had this double arrow there with the total variation distance, but it's like one direction seems to be easy to see, right from right to left, right? But from left to right?
Yeah, it's a good point. Yeah, so I decided to skip talking about it, but let's actually do it given that you asked the question. So one equivalent way of thinking about Hamming distance between two sets of endpoints is to consider the total variation or statistical distance between the uniform distributions, so discrete uniform distribution on X and Y. And then you can convince yourself that X and Y being at most epsilon away in Hamming distance is equivalent to the uniform distributions on X and uniform distribution on Y being epsilon away in total variation distance. Does it make sense?
Yeah, that makes sense, yes.
Okay, perfect. So, let me instantiate this, outline of an algorithm in this strong contamination model by taking the example of mean estimation that we saw earlier. So remember the setting, we get like a corrupted sample from some distribution D, and we would like to estimate the mean of the distribution D, okay? And notice that, of course, you can't quite use empirical mean of Y because that can be arbitrarily far off from X. So let's implement the outline we had on the previous slide. We would first like to make some reasonable assumption on the class of distributions D comes from. Now, even in the setting without outliers, we know that we need, for example, the variance of D to be bounded in all directions, or equivalently the spectral norm of the covariance of D to be upper bounded, in order to apply, let's say, standard concentration bounds like Huffington's inequality and get some estimates for how far the empirical mean is from the true mean. Okay, so let's say we make exactly that assumption, on D. So now let's say we know that the spectral norm of the covariance of D is at most 1. Okay, so this is our class of reasonable distributions, the set of all distributions whose covariances have spectral norm at most 1. Notice that they can have arbitrary means, but only the condition on covariance is actually being made here. Good. So now how does our algorithm look like in this context? Well, we would like to find a set of endpoints X prime whose empirical covariance is upper bounded by 1 in spectral norm, and X prime must intersect the input Y in all but an epsilon fraction of the points. So equivalently, you can think of the problem as taking Y and having the freedom to modify any epsilon fraction of the points in Y so that the resulting points have an empirical covariance which is upper bounded in spectral norm by 1. Okay, and then once you found, I don't know how you're going to do this, but once you found such an X prime, you simply return the mean of X prime. Okay, so you can ask, how is this particular inefficient but well-defined method going to do for estimating the mean in this setting? So here's a claim that I won't prove. Actually, it's actually not even hard. It takes me like 15 minutes to prove this, but I don't have those right now. So I'll just make the claim and and move on. So in the previous slide, we had to somehow bound the distance between the parameters of X prime and that of X. Here the parameter is mean. We would like to bound, let's say, the L2 distance between the mean vectors of X and X prime. Okay, so here's a claim that says that this distance is bounded above by some constant times square root of the total variation distance between the uniform distributions on X and uniform distribution on X prime. In other words, in our setting, given that X and X prime are, let's say, 2 epsilon away, this bound gives an upper bound of O of square root epsilon on the L2 distance between the means of X and X prime. Okay, and now notice that this is a rather non-trivial bound, because even though we are in like D dimensions, the error that we are making in estimate of the mean is independent of the dimension. It only depends on epsilon. There is no dimensionality that enters the error upper bound here. Moreover, you can prove that if the only thing I know about the distribution D is that its covariance had bounded spectral norm, then up to some dimension independent absolute constants, this bound is in fact information theoretically tight. Okay, so basically this claim proves as good a bound as you can hope to prove when the only thing you know about X and X prime is that they are TV closed and have bounded variance. And so that's it, right? Like we've already found an algorithm which is highly inefficient, but at least give you a reasonable estimate of the mean in infinite time, let's say. And in order to make this efficient, you would want to somehow find like a good or efficient representation of the class of reasonable distributions. Here, that is simply the class of all x prime whose empirical covariance is upper bounded by 1. Now, I don't want to belabor this point too much, but in this case, a semi-definite representation kind of follows. It's not immediate, but it follows from the observation that the condition that the covariance of x prime is at most identity, which is equivalent to saying that the spectral norm is at most 1, is almost by design a semi-definite condition. Okay. Good. So that was the instantiation of the paradigm that we saw for mean estimation for bounded variance distribution. Now just to give you another example, let's say that we wanted like a better guarantee than O of root epsilon. Now, as I told you, our guarantee is tight if the only thing I know about the distribution is that it has bounded variance. So we would have to make some stronger assumptions. Okay. So let's say that this time we know that the unknown distribution is 4 sub Gaussian. By 4 sub Gaussian, here is what I mean. If you look at this inequality that appears inside the ball over here, the second inequality, by the way, is the same inequality we had earlier, which is that the covariance has bounded spectral norm. It's just written in this funny way. But the first one is the additional condition we are assuming now. We are saying that in any direction v, if I project the center distribution, so x bar is x minus the mean of x, then the fourth moment of this 1D random variable x bar dot v is upper bounded in terms of the square of its second moment. Okay. So the fourth moment is like not too much larger than square of its second moment. Okay, that's what I mean by sub Gaussian inequality for fourth moments. And in order to remember this constant c, I would call this distribution, let's say c sub Gaussian for now. Okay, so this is clearly a stronger condition because I've assumed something more, and in fact I've made an assumption about fourth moments of the distribution rather than just second moments in the previous slide. So let's say we did the exact same thing as on the previous slide. So, we would actually end up with the problem of determining the distance between the means of two distributions, which, satisfy this extra condition of 4 sub Gaussianity, and we would like to understand what's the difference between their means. And it turns out that we can actually prove a slightly better bound. This time we can prove that the L2 distance between their means grows as epsilon to the 3/4 up to some fixed absolute constants. And so now epsilon to the 3/4, if I got it right, is smaller than epsilon to the 1/2. So we've made some improvement. And again, you can prove that this is basically information theoretically optimal. So it's as good as it gets up to some absolute constants that appear, multiplying this epsilon to the 3/4. And again, in order to make this into an efficient algorithm, I would want to find like some convex or efficient representation of the set of reasonable distributions here. This time my reasonable distributions are defined by this, almost suggestively speaking, polynomial inequality that, in every direction v, the fourth moment is upper bounded by square of the second moment. Okay. So let's investigate this thing a bit further because this is basically where polynomial optimization enters in some full force. Okay. So let's, make this extra definition like an extension of this definition of sub Gaussianity. And, this is going to be what our notion of efficient representation would mean. Okay. So I'm going to call a d-dimensional distribution t comma c sub Gaussian if it satisfies this inequality of the form I wrote on the previous slide for the special case of t equals 4. This constant, in general, has to grow with t, and in fact, I'll justify very soon why it has to grow like at least t to the t over 2 for reasonable distributions. So it's just parameterized in this way because that's what reasonable distributions look like. But think of t as an absolute constant, in which case this is like some fixed constant over here. Okay. So far there is no difference except that there is this addition here, where we say that this inequality has an SOS proof in variable v. Okay. So I'm sure that all of you already know what this means, but let me clarify this just in case. So having an SOS proof of this inequality in variable v means that if I take the right hand side, subtract the left hand side, then and view it as a polynomial in the vector valued variable v, the d-dimensional vector valued variable v, then it's a sum of squares polynomial. Okay. That's what I mean by having an SOS proof of this inequality. Now notice that this is clearly a stronger requirement. If there is an SOS proof, if there is an identity of the form that holds, on the second line over here, then certainly the inequality is true. But inequality being true in general would it not in general imply that there is an SOS proof? So this is a stronger condition than just being T, C sub Gaussian. Okay. So that's, this condition, we formalized it in this work with David Steurer from ETH at Zurich, 3 years or so ago. And we call it certifiable sub Gaussianity. So, this kind of looks like a crazy condition. We are demanding an SOS proof of a funny inequality. So, one might wonder whether it's even, legit to expect that reasonable distributions actually have such an SOS proof. So let me, allay some of those fears. Actually, first, let me observe that, once you have this SOS proof, again, I won't go into too much details. And for you, probably I don't have to. You can use the existence of this sum of squares, proof of these inequalities to give efficient semi-definite representations of the reasonable class of distributions that we saw on the previous slide. Okay, and so that's basically the intent behind defining this certifiable variant of sub-Gaussianity. So coming back, here is like the first quintessential example of a distribution that satisfies this certifiable sub-Gaussianity property. If you compute the tth moment for a Gaussian distribution with an arbitrary covariance, then in fact, the tth moment of it in any direction, in fact, satisfies an equality where this c t to the t over 2 is in fact t minus 1 double factorial, which roughly grows like t to the t over 2. And so, we have an exact equality here, which means that the difference of the right-hand side and left-hand side is 0, which is, a trivial sum of squares polynomial in V. So, we actually satisfy this definition over here. And indeed, the algorithm in the previous slide actually works for Gaussian distributions. But actually, there's more. This property, just by eyeballing it, you can see is invariant under affine transformations on X. Actually, linear transformations might be immediate. So if I linearly transform X, that new random variable continues to satisfy it. But in fact, you can even prove that, additive shifts also do not change it. So, that requires maybe like a 2-line calculation, but it's also true. And in particular, it holds, and because, it's a fact only about tth moments of the distribution, it actually continues to hold for any distribution which is, t-wise uniform, as in like there is no correlation between any subset of t variables. Okay, so that's some reasonable set of distributions that already satisfy this inequality, the certifiable sub Gaussianity inequality. But you might wonder that these are kind of boring distributions. Like no real distribution which has like correlations between the variables is captured here. So let me, give you one result, and in fact, the only result that we know in this direction that goes beyond these simple classes of distributions that satisfy this inequality. So in this paper with Jacob Steinhardt from Berkeley, we proved that, in fact, certifiable sub Gaussianity holds for any distribution whenever it satisfies a certain analytic inequality called as a Poincare inequality. So very roughly, a Poincare inequality on the distribution D says that, Lipschitz functions of the distribution satisfy a certain dimension-independent concentration. So their variance, is upper bounded. But, don't have to worry too much about this. Let me just mention that one corollary of this theorem that we had with Steinhardt is that certifiable sub Gaussianity, meaning the sum of squares proof of this sub Gaussian inequality, holds for all strongly log concave distributions. This you may have heard about. If not, all this means is that if you take the probability density function of the distribution, take the negative log of it, then it's a strongly convex function. Okay, that's all it means. And so this is like a wider class of distribution than just Gaussians, and it allows for like non-trivial correlations to exist between variables. And what we have is that there is a sum of squares proof of sub Gaussianity for such distributions. And so as a result, we get so I'll show you a slide very soon where we get several algorithms that work for all certifiably sub Gaussian distributions. And so all the examples I wrote on the previous slide are the distributions that our algorithm works for. So here's the first open question that I suggested at the beginning of the talk, which is simply at a very high level to find more general distribution classes that satisfy certifiable sub Gaussianity. Okay, and as I'll soon show you, if you do this, then a number of algorithms automatically get upgraded. Once you have like this proof of certifiable sub Gaussianity for like more general distributions. And notice that this is like a purely algebraic statement. This is a statement about a certain inequality having a low degree sum of squares proof. Okay, so one concrete question in this direction is to prove that all log concave distributions, not strongly log concave, only log concave distributions satisfy certifiable sub Gaussianity. We actually kind of already know proof of this if we assume this so-called the Cannon-Lowasz-Simonovitch Cooling conjecture. But there should be like a standalone proof of this, and so that's the open question that I'm suggesting here to prove this fact for log concave distributions. Actually, there is a very recent progress on the KLS conjecture by Chen. It doesn't completely resolve it, but it actually makes a big improvement. So already, there is the algorithm that we have extend with some weaker bounds to all log concave distributions. Is there a question?
Yes.
Yes, there's a question, Pravesh.
Okay, go on.
So you told us basically that among all distributions, we can write down the certifiable sub-Gaussian ones by a semi-definite condition, right?
Yes.
But the question is, of course, in your meta algorithm that you sketched beforehand, afterwards we want to find a distribution, right? So if we just write down the sub Gaussianity condition, then we will not get a distribution, right? We will we can maybe get a square definite functional or something like that.
Yeah, it's a very good point. And among the several details I have swept under the rug, this is also one of them. So we are not really required to find the distribution itself. We are only interested in the moments of such a distribution. Actually, we don't even need moments, to be honest. But the following fact is true, which is that as long as the certifiable sub Gaussianity property has a sum of squares proof, the outline that I gave on the previous slide would extend to all those distributions. You're right that the description I provided wasn't very clear about that, but that's a compromise I made in making this talk.
I'm just interested in the question. So what happens if you'd actually then in the end up with a functional that gives you some say pseudo moments, that are not actually originating from a distribution, right?
Yeah.
So you'd need to somehow tackle this case that then they still need to be close to actual moments.
Yeah.
Right?
So that proof already exists. We already have a proof that the pseudo moments would be close to the pseudo moments of the distribution that X is chosen from. So we already know that if X is certifiably sub Gaussian and X prime is epsilon close to X in like Hamming distance, then the pseudo moments of X, or whatever you compute from this relaxation. The pseudo moments of the relaxation solution would be close in the appropriate sense to the actual moments of this unknown original IID sample X.
So what saves us here is then basically the initial constraint that we are close to this observed distribution Y,
absolutely,
right?
Absolutely.
Okay.
It's very important here. Yes, you're right.
Okay, so because we basically have a local ball constraint. Okay.
Yes. Yeah. So it's in some sense it's like a local version of a statement that we would like to be true globally, but we don't know how to prove.
Okay.
Perfect. Okay. Very good. So here is basically a list of so here's the list of problems that I showed you at the beginning, and I've just marked the ones that depend only on certifiable sub Gaussianity, which means that if you actually make progress on this conjecture on the previous slide or the open problem on the previous slide, you would automatically improve this algorithms for 4 + 2 6 different tasks in this robust statistics literature. Good, very good. I'm actually much slower than I expected, so what I'll do is like give you a very quick overview of this second type of algorithm, and get to the open question because I still want to get to it. That's the most interesting part here, for this audience at least. So. Remember I told you the second model, which was about list decodable learning. In this case, we not have 10%, but have like 90% outliers. So, almost all of the samples that we see are garbage. And we would still like to somehow, we would still like to design an algorithm that can, learn like a small list of parameters such that one of them is close to the truth. Okay. So the outline for, designing algorithms in this model, we have like fewer than, the previous model, but still like, let's say at least 3 algorithms in this line of work. They all, look kind of similar at a very high level to the previous outline. I'll point out the difference very soon though. So, just like the previous outline, we, make some reasonable assumption on the class of distributions D that, the original sample X is chosen from. Notice that we never make any assumption on the outliers. They're always like arbitrary. Then, we know that Y is, this time it's not epsilon, but like 1 minus alpha far. And this notation is chosen to remind you that, Y and X are very, very far here. Like they're like, different on 90% of the points. So if all you do is find like a single X1, which is also 1 minus alpha, away from Y, then triangle inequality tells you nothing. X and X prime could be like different on every point. Nevertheless, you can show that if instead of finding a single X1, you find like a O of 1 over alpha size different Xi's, which are separated from each other, then one of them would be about 1 minus alpha close to X, okay? Now, because this is not the main point of what I want to go to, I would not give you too many details of how this is proven, but think of this as like some not so hard combinatorial argument. Okay, so no matter how we do it, we can argue that if you find like a small list, then there is one member of this list which is like 1 minus alpha away from X, meaning that it matches X in at least an alpha fraction of the points. Okay, and it's a reasonable distribution itself. So X1 prime is inside this ball and is different from X in at most some alpha is different from X in like at most 1 minus alpha fraction of the points. Okay, and once we have that, we output the parameters of X prime just like in the previous outline. So just like in the previous outline, the analysis has to analyze the distance between the parameters of X1 prime and X. This time when the distance is like 1 minus alpha, which is like much larger than half or whatever. And to make it algorithmic, we would have to find efficient representations of the reasonable class of distribution that we've chosen. And we need certain more things here, which let me ignore. Let's focus on this part because that's where algebraic geometry comes in. So let's think about what kind of distributions arise in this context, and what actually entails when you want to find out efficient representations for membership in this class of reasonable distributions. Good. So let me take this example of list decodable linear equation solving or list decodable regression problem. It's a very simple problem. So, in this problem, the original sample, so before corruption, looks like, a bunch of points, which you should think of as like coefficient vectors of an equation and, the right-hand side of the equation. So think of L star as like an unknown solution, which was used to generate this satisfiable subset of equations. And each equation looks like, X1 is the coefficient vector, d-dimensional vector. And, the right-hand side of this equation is like, the evaluation of L star on X1. And similarly for X2 and so on up to alpha n. So they're like alpha n uncorrupted soluble set of equations where L star actually solves them, okay? And you get a corruption Y of it. And you're, interested in finding a 1 over alpha size list of parameters such that one of them is close to L star, okay? So here is, quickly getting to the main point. The main question we are interested in is, suppose X and X prime are, two sets of equations, n equations that agree on an alpha fraction of the equations. By agree, I mean that the right-hand side of the equations are the same, okay? Imagine that we have solutions L and L prime for X and X prime. And let's say that, they are in general different. We are interested in understanding how far can L and L prime be, given that, X and X prime agree on an alpha fraction of the equations, okay? So here's a small thought experiment. Say L is a solution to this, X prime. Then for every coefficient vector of an equation X in X intersect X prime, both L and L prime, so let's say L star is the solution to, X. So clearly L star solves those equations correctly, the one in the intersection. And we know that L is a solution to X prime. So for all X in the intersection, both L and L star correctly solve the equations, which means that if I evaluate L minus L star, the dot product with X, for every X in the intersection, it must be 0, okay? And so, I would like to somehow have some notion of reasonableness or assumption on the distribution D so that this property cannot happen for any non-zero vector, okay? In which case I would be able to conclude that L minus L star is 0 or L is equal to L star, and then I would be happy. So here is the relevant property, cutting to the chase. I would want the property that if V is any non-zero vector, if V is any vector such that V dot X evaluates to 0 on the distribution more than an alpha fraction of the times, then V is 0. So, no non-zero vector can evaluate to 0 alpha, more than an alpha fraction of the times. Okay. Now this is like a well-studied property in probability theory, but it kind of arises naturally in the context of the linear equations. And getting to one final slide, I'll just take one more minute to get to this open problem. So here we need like a certificate of this property, like an SOS certificate of this property. And so just like we defined certifiable sub Gaussianity before, here is the relevant definition over here. We call a distribution X, a finite set of points X, certifiably anti-concentrated if there is a degree T sum of squares proof of this implication. So, I have a bunch of polynomial equality constraints on the left, implying a polynomial inequality constraint on the right. And roughly, the polynomial equality constraints on the left encode the fact that W's, identify a subset of the points in X such that there is a direction V which is non-zero. And, whenever Wi is 1, so Wi square is Wi, meaning that it can only be 0 or 1. And whenever Wi is 1, xi dot V is actually 0. Okay. And so what the implication says is that if you find a subset of points where there is a non-zero vector V that projects to 0, then the subset of points must not be more than delta. Okay, so only a small number of points can actually have this property that it projects to 0 in some non-zero direction. We show that in fact this property, that there is in fact a low degree sum of squares proof of this property for Gaussian distributions, and that's roughly all that we know here. So it's like much less understood than certifiable sub Gaussianity that I showed you earlier. And so, there are a couple open questions over here. One basically asks you to prove this property for log concave distributions. I believe it is true, but I don't know how to show it. And the other open question is trying to improve the sum of squares degree bound for, even the Gaussians that we do know at the moment. So, a lot of problems can actually solve with just, these assumptions on the distribution. So, improving our understanding of these properties would upgrade all our algorithms at once. And, I was a bit quick at the end, sorry about that. But, if you want to actually get a better understanding of how this area works and how polynomial optimization plays a role, you can either look at this monograph, which we wrote recently, like a couple of years ago, or, there is like a updated version, which I taught in my class in fall of 2020, and all the materials are public. Okay, sorry about going a little bit fast at the end, but that's the end of my talk.
Thank you very much for your nice talk. Do we have questions?
May I ask a question?
Yes, of course.
Hello, Pravesh. So actually, you were always talking about distributions, and when you take a sample of size n from a distribution, but what do you actually handle in the algorithms? Do you actually work with empirical moments of these distributions?
Perfect.
But when the size n does not actually appear somewhere, or?
It's an excellent question, Marcus. I actually shrugged a lot of details, unfortunately, to get to the open questions. But you're right. We don't actually work with distributions. We work with the moments, just like you suggested. And the size n plays a role only to the extent that I have to phrase the constraints that x and x prime, must intersect in all but an epsilon fraction of the points. So the size does play a role over there, but no more beyond that.
So if you want to carry out the algorithm, actually, so the n does only appear when you compute from your input, from the yi's, some empirical moments, or?
No. So let me, let me actually just describe to you what the polynomial relaxation is, because then it will become clear. Okay. Yes. The variables of my relaxation would be x prime. So I basically have variables for this sample that I'm trying to invent. Okay. So these are like n d-dimensional points. So they're like n times d real variables.
Okay.
In addition, I would have, indicator variables w1 through wn. And, this is basically one per sample. And now my constraints say that, whenever wi, so I'll have the constraint that wi square equals wi, meaning wi's are Boolean. And further, that wi times xi minus xi prime is 0, meaning whenever wi is 1, xi must equal xi prime. Okay. So now you see that with this system of constraints, I have enforced that x and x prime must intersect in all but an epsilon fraction of the points. I mean, I need to add the constraint that sum wi is 1 minus epsilon times n. But that's it. Okay, that's the description of my reasonable class of distributions, which is at least, I described to you the intersection constraints, and then in addition, I would have to force that, let's say, for example, here, I would force that the empirical covariance of x prime is upper bounded, which is, a semi-definite constraint, or equivalently like, a system of polynomial inequalities. In the other example I gave you, I would have to enforce, this certifiable sub Gaussianity constraint. But, I actually have variables for both x prime and the intersection of x prime and x to actually encode all my requirements.
So if n is big, you get a really huge SDP.
Yeah, yes. So let's see, did I say that somewhere here? So the size of the representation would be, d times n to the O of t. So remember that I was interested in finding an algorithm which is polynomial in d, which, let's say, between friends, we agree is efficient. I agree that it's not like, efficient in real life or whatever. So, as long as t is a fixed constant, so this like the number of moments or whatever, like the level of sub-Gaussianity that I needed is a fixed constant, this in fact would give me an algorithm which is just like d to the O of t. And so if t is a constant, we can actually happily go home and call it a polynomial time algorithm.
Yeah. Okay.
That's basically the intent here. Does it make sense?
Thank you. Yeah.
Perfect. More questions?
Yes, are there?
Yeah, I have a question. Hi, this is Corby. I was wondering, are you only interested in like a feasible sample set, or are you also trying to find an optimal one? For example, maybe like in a maximum likelihood manner, for example.
Excellent question. So, okay, that's a very, very good question. So in this context, I am not 100% sure that we can actually do much about the maximum likelihood estimation. And here is the reason why, okay? Notice that, okay, so, when you want to do maximum likelihood estimation, you usually need a prior on, I think, the error model. In our case, the errors are completely adversarial. There is no, statistical or probabilistic element to them. The epsilon fraction of the points that are modified, they can be modified completely adversarially. So for example, imagine the following process where, I generate an IID sample from, our distribution. Then I hand it over to a malicious adversary who looks at the whole sample and, let's say even knows our algorithm and tries to modify an epsilon fraction of the points in order to fool our algorithm. So the point I'm trying to make is that there is no prior on this epsilon fraction of the modifications that the adversary is doing. So in that context, I'm actually not sure that you can do much more than what we are actually already doing, because in principle, any element of this reasonable class of distributions could have been used to generate Y.
Okay, so you don't think it's possible to like look for a sample that is this epsilon close and whose maximum likelihood for this sample is maybe maximized? This doesn't make sense.
It actually, okay. So I guess in a maybe to the okay. I guess it does make sense. At least the gap might be that in the formulation I have, I'm only using some basic properties like x has bounded moments of temper, while the maximum likelihood in principle could make use of more statistical properties. So you are right, like in principle, this relaxation could do something slightly different. But yeah, I have no idea how good it is. My suspicion is that it's probably no better because, in some sense, it seems like there is not much to do except moments here, but I could be wrong. But I guess the even bigger issue might be like how, if at all, would you do such a maximum likelihood estimation efficiently, which again, I have no idea about.
Okay, cool. Thank you very much. And thanks for the talk.
Yeah, thanks for the question.
I have a question. Have you used this approach in practice to do some
yeah, that's
and how is it behaving?
Yeah, that's an excellent question, Bernard. And I have basically only embarrassment to report. So, yeah, these methods are highly inefficient right now in practice. So the sum of squares based method are actually highly inefficient. We actually can't quite run even degree 4 SOS relaxations. So what has actually happened is that people have been able to take some of these high complexity semi-definite estimation algorithms and design some versions of them which actually do not involve solving semi-definite programs, but kind of give you the same guarantees and are much faster. So there is this whole line of work on speeding up SOS based or semi-definite programming based algorithms. And in the context of robust estimation, this has been done in like a couple of papers, which is like mentioned at the bottom of this slide. And so I would say that these algorithms are actually very efficient. You can run them in the practice for, let's say, like dimension which is as large as maybe 1,000 or so, which is not great but still reasonable. The SOS based algorithms, the ones that I kind of describe a blueprint for today, are horrible in practice. So yeah, I don't recommend running them.
So the speedups that you mentioned, they are what kind of speedup it is? So they relax.
Very good. So okay, so first of all, what they do is so when you think of so imagine that you write down this SOS relaxation. It's a certain semi-definite program. Okay, now what this speedup results argue is that for the specific context of some problems, so for example, I think this is known for mean estimation, you can prune the SDP, you can remove many of the constraints, and then instead of solving SDP exactly with, let's say, an interior point method, or by exactly I mean like with like logarithmic convergence, you in fact try to solve it like with some more imprecise methods like multiplicative weights or whatever, which are which have a slower convergence, but they do reasonable in the context of our problems. So that's basically one way you can actually get much faster algorithms. They first of all prune the SDP, and then they don't use interior point methods to solve SDPs. They instead use multiplicative weights to approximately solve the SDPs.
Okay, thank you. I see. So do we have other questions?
Yes, so maybe I can ask a question. Like as a follow-up to what you said. I mean, like, do you know if any methods like maybe SD cells were used to solve that kind of problems, because they're like much more efficient in practice? They use kind of like different certificate, but do you know if anything in this line was studied in the literature so far?
Yeah, Adam, I'm not even sure that I know of this SD SOS based method. So, but you're absolutely right. Like, I think they might actually be a great set of methods to try in the context of implementing these algorithms. I'm pretty sure they haven't been tried.
I see. Okay, thank you so much.
Yeah, one of the reasons I'm actually excited to give this talk is because we have this whole new set of experts who actually might have very non-trivial and interesting things to say on this problem. So I'm glad you brought it up.
Okay, thank you.
So can I have a question?
Yeah.
You said make some of the SDPs smaller, so by pruning. But even after pruned, they are still too big for integral point solvers.
Yeah. So one of the things, so you're right. Like even after pruning and even after solving them approximately with multiplicative weights, you're right. Like there is this issue of memory, which is that the solution to the SDP might just be too big to store in memory, and that already might actually pose a hurdle. So what these methods do is that they actually don't store the whole SDP solution in memory. And that really requires, using very problem-specific properties. So for example, in the context of mean estimation, what these methods do is like they somehow only store a vector, which is kind of crazy. Like the solution to our moment SOS program, for example, was like, a set of first, 4 moments, let's say, of the distribution that we are trying to estimate. Instead, these speed-up-based methods only store the mean vector if you're interested in estimating only the mean vector. And somehow, they are able to, do these SDP manipulations implicitly. Like, instead of storing the whole solution in the memory, they are just going to do these manipulations implicitly. Now, this is not a generic method. You can't quite hope to do this in general for solving SDPs. But, in the context of these specific problems, it tends to work out. So these are like somewhat non-trivial and like not so simple papers, but that's roughly what's going on in them.
All right. Thank you.
Thank you. Other questions? if not, we stop here. Thank you to every speakers of the day, every participant of this workshop. So this is the last day of our workshop. The slides and the video will be available on the website.